to the course here, which is tangent space. Now, how do you think? So, intuition is very important in differential geometry, topology, everything. Intuition is very, very important. Without intuition, you can't do geometry. So what is the tangent space intuitively for a surface? So, suppose you have a surface. Something like this. You have a surface. And you want to look at tangent space. So, what is your intuition? Yeah,
It's a plane passing through that point.
plane passing through that point. Yeah, so how many planes are there passing through that point?
Infinitely many.
Infinitely many. Which plane would you like to take?
Sir, if you think of it like a bowl and place it on the floor.
Say that again.
Think of it like a bowl and place it on the floor.
Yeah.
Floor is the tangent plane.
That is true in some certain sense, yes, but the point is your bowl need not be a surface, smooth surface. It might have corners, right? Yep. Of course, the point, so how many points it will touch to the floor?
Locally only one.
Well, in general, that kind of bowl you have not seen, right? In practice, it doesn't happen, right? Does it?
In some neighborhood, it's intersect only one point. It's like something.
No, in physical bowl, so for example, when you take some curry and these things, so does it intersect floor at only one point?
Sir, it may be flat at that place, but
Yeah, I mean it is flat. Otherwise, it becomes unstable, right? So you can't work without this flatness. So when you take some things from there, it will just move around, right? Move around and fail all these things, whatever curry. So to get the stability, one needs a little bit flat down there. So yeah, but tangent space. But you better think of yeah. So but without doing anything, if you just keep an empty bowl, which is round shaped. Let's say better example would be a kadai where you cook, right? Circular shaped, and you put there in the floor. Well, it may not be stable, but tangent space doesn't need to be stable. Tangent space is there, and you are not looking at the dynamics, so you don't worry about whether it is moving or not, whether it is stable or not. But yeah, then floor would be a tangent space. So you want a plane which passes through just only one point, right? Or touches the surface, right? Tangent space, it should touch the surface, it should not intersect, right? The point is, it may not be always that it will intersect only one point. So suppose you have a plane, art plane in, let's say, XY plane in R3, right? Suppose this is the plane. This is your manifold. So M is x comma y comma 0 in R3, right? So this is, now what is its tangent space? It is itself at every point, right? Any question here? It touches at infinity many points. Almost actually everywhere. So you look at, instead, if you are not comfortable with taking at XY plane whole, you look at an open subset here. An open subset. U. Open in N. So an open subset of a smooth manifold is again a smooth manifold that you already know by now. So look at its tangent space. It is whole N, whole XY plane, right? It also intersects the tangent space everywhere. So it need not be true that tangent space must intersect only at one point locally or non-locally, whatever. Right? The question is, you need to make sense of that it touches. It touches the surface, it touches the manifold. That is more important than having intersection at only at one point. I mean, a flat surface will have, it might have more than one point at which it might intersect. All right? Any question here? Any question? All right. So, for example, so let's look at R3 again. So tangent space of a surface is a plane, right? Tangent space of a surface is a plane. Well, we have not proved that yet, but you might have seen it in curves and surfaces course, right? So tangent space, well, suppose you have a surface and you want to construct such certain plane, which might give you the tangent space. So let's first look at any plane that intersect the surface. So how many points one needs to actually determine a plane in R2, R3? How many points you need to determine a plane in R3?
3 points,
3.
but not on a straight line.
Right. 3 points. 3 points you need to determine a plane. Right? Suppose you have something. Yeah, you have like this. You add some points here. Let's take a different color. This is 1 point. This is 1 point. This is other point. Right? So you want a plane.
So we can also tell with 2 points, right?
You can
Also find a plane with 2 points.
also find
A plane uniquely with 2 points.
unique
cannot-
unique plane passing through 2 points.
Not passing through 2 points, but with just 2 points.
I didn't get your, I mean, what are you saying? So, but by 2 points, you can determine a plane?
Yes, sir.
How?
So one is a perpendicular,
Hmm.
and the other point will be just any point in the plane. So that will give you the affine like transform.
Yeah. So, what is the problem here? So, in this approach, what is the problem? Can you tell me? Right. So, then you might have heard, I mean, you need a three, and for determining a plane, you need 3 points. Right. But as Horsit argued, you might have with 2 points, right? So, what is the fallacy in this argument? Or what is the, I mean, what is, uh, so what is this 2 and 3 points, this argument? How does this argument matches, rather?
So can you repeat Harshit's argument?
He said, I mean, you can determine a plane by 2 points. One, a plane passing through that point. Other is perpendicular to the plane.
So when I say perpendicular, it's like the direction with respect to the origin. And
Right.
the other point is just for giving where is the plane.
So,
origin you are taking 1 point. Is 1 point, right? That is 3 only.
No, we're not taking origin to be a point in the plane. Like we're taking origin as a reference. That's all.
So what?
yeah, Praful.
So the perpendicular means we are indicating a direction, which requires 2 points.
No, that's why I'm
Yes, yes.
taking the origin. Like the point to the origin is the perpendicular.
What do you mean by point to the origin? You mean direction to the origin, like the line joining the origin and that point as a perpendicular.
Okay.
Exactly.
So-
So he's not taking 2 points. He's taking one vector and 1 point. That is the distinction between a vector and point. Right. So yeah, you since Rn it's already a vector space as well as metric space. So the points when you are considering, you are saying that 3 points is required to determine, or you can determine a plane if and only if it passes through 3 points, 3 non-collinear points. So what it means is basically you are looking at in the sense of matrix space, and of course the planes is a planing is a right. So plane comes from definitely of course a vector, but you can define the plane as you do, and you incorporate it in terms of metric spaces with 3 points, and that's what it was saying. But when you consider one vector and then 1 point, so this is something different. We are using quite a bit. I mean, you are using a vector which is normal, and a plane and a point passing through the plane that lies in the plane. Yeah, so it doesn't. It actually. So it means that. Uh, it means that. So you are combining vectors. You're combining vectors here, And as Rakhal said, that for vector you need two points, but of course those 2 points might not lie in the surface or in the plane. It's true. That is definitely true. But yeah, so one vector is required. So one vector, 1 point, or you need 3 points. These three are same. So having 3 points, you'll get actually such a vector as well. Now the point is, you fix a point P and let this 3 point goes there. And how does the plane will move, right? So the plane will move towards this, and that could be on intuition or tangent space, right? As the point here, this is called second plane. This plane here, as this point, and that point moves towards this, then what you get is the tangent plane. Right. That could be one intuition, but of course, all this lying inside R3. So you need an ambient space R3 here. And so in case of Rn, you could do the same thing. But for a general manifold, you might not have Rn. Right? So you need to distinguish the properties which does not depend on the ambient space, and then try to define tangent space independently. And that's where this derivative vector comes in, what we'll call here a derivation, right? So anyway, I told you to read chapter 1. Have anybody read section 2 of chapter 1?
I read, sir.
Yeah, so that would be our next thing. So here in section 2 of chapter 1, so section 2, chapter 1. So who have not read, please read it here of Tu's book. It gives a way of defining tangent space of Rn, which can be generalized for the case of smooth manifold. So what is it? Again, as Arundhati was saying, so you need to look at derivative vectors. That's very good. So it means directional derivative. So corresponding to a vector, you get a direction. And then the following, suppose V is a vector in Rn, right? And then and F from Rn to R, a smooth function. C1 is good enough, but anyway, it's fine if we take C infinity. Then we can define the directional derivative around V as dvf, right, which is at some point a, is limit t tends to 0 f of a plus tv minus fa by t, right? This you have seen in your calculus in RN or analysis 3 course, right? Yeah. So how can you write this thing? So this is, let's go back, let's go to the next page. So suppose V is V1, V2, Vn. Suppose V is V1, V2, Vn. Then we can write dVf at A is summation Vj del f by del xj at A. Is this correct? Everybody is clear about this? This is by chain rule. So what you are looking at is the following. You can correspond dV to something here, j equal to 1 to n Vj del by del xj. So d nu is dV is an operator, right? So this is also an operator. So d mu at let's say at P, you can write this at, right? This is it. This is at P. P is a point in Rn, or sorry, A. In our case here, A. 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 Now this is something important. This is important. This notion is very important. This notion you might not have seen yet. In analysis 3 course, of course, you have not seen. So this is an operator on the space of C-infinity smooth functions on a neighborhood of A, right? Does this make sense? So you apply dV on C infinity. Let's say A. I write A because it is in a neighborhood, any neighborhood. We are not fixing a neighborhood to R. So dV at A. Now is this, the point is, you might have the same thing, right? Same derivative for two functions, right? You might have the same derivative for two functions around at P. True. So this one, we want to find an analog to this one in case of manifold, or rather we need to, this doesn't have anything to do with coordinates or anything to do with the tangent plane or anything, right? Any ambient space. So this one we want to generalize, right? So it gives you, when you apply a function, it gives you the directional derivative along the direction v, right? Now we'll construct, we'll look at these things. So this one, what is this one? This one determined by its action on the space of infinity functions here. So this one, this v gives you a tangent vector that actually we can define that to be a tangent vector. All right. So just 1 minute. So next term is, so next we define an equivalence relation in the space of C infinity function in a neighborhood of a point A. And then we look at the concept of derivation. All right. So this one we'll do next time. So maybe that's it for today. We'll do it. Yeah.